Hi everyone, I'm Radoslav, and today I'm going to be explaining the solution to one of the problems for the last CodeChef, which the CodeChef Cook Off that happened this Sunday. And I'm going to be talking about the joint subarrays on tree problem. So yeah, here is again a slide about me, but I guess let's just get straight to the problem statement. So basically, here is like an outline of what the solution would look like. First, I'm going to explain what the problem was, like this problem statement. Then I'm going to be talking about the solution for a particular subarray. And as the problem is on trees, you could have, I guess you could have guessed it from the problem statement. And yeah, I will first start by explaining the solution if we had a chain or just an array. And after that, I'm going to be explaining how to actually extend it to a tree using some data structures. And finally, I'm going to be talking about the intended solution, although like the last 2 points are actually, they have the same complexity and both should be fine for an accepted solution. So yeah, going to the next point, basically let's go to the problem description. So I'm going to go to my browser now. Okay, so basically what we have is we have a, first we define a function f, which is defined for some array A, and it will basically be defined as follows. We choose two non-intersecting subarrays, and then we concatenate them. And if this final array, which is like the two subarrays concatenated, is non-decreasing, then, I mean, like we want to choose two subarrays such that their concatenation would be non-decreasing. Or in other words, like more formally, we choose 4 indices. The first one is I, then we choose J, then we choose K, and then we choose L. And they should be like follows. So it's basically, I mean, I and J will define the bounds of the first subarray, and K and L will define the bounds of the second subarray. And those two subarrays should be non-intersecting. And we want to have both of the subarrays non-decreasing, and also the last value from the first one, so ij, should be less than or equal to ak. Or in other words, we just want the concatenation to be non-decreasing, because we know that from the choice, we want the subarray from k to l to be non-decreasing, and we also want the same for the one from I to j. So in other words, and we also want to have like ij being less than or equal to ik. So basically, this means that we want to have like the whole concatenation being non-decreasing. And the weight function, or like the value of some subarray, is defined as j minus I plus 1 plus L minus K plus 1. But here you can actually notice that the first thing is the length of the first subarray, while the second one is the length of the second subarray. So in other words, we want to choose two subarrays such that for like some choice of two subarrays, so that their concatenation is non-decreasing, the value will be the sum of the two lengths of the subarrays, or in other words, the total number of elements we chose. And the problem basically asks, so like, actually we are still in the definition of f of this array A. So f of A is basically the maximal weight function for every possible choices of two subarrays. Or in other words, it's f of A is defined as from all possible choosings of two subarrays, find the one which has most elements. And like the answer will be the maximum number of elements we can choose, like the total number of elements, which is the number of elements in the first subarray plus the number of elements in the second subarray. So yeah, basically that's how we define f of A. But I mean, the problem is on trees. So actually we are gonna extend this thing for trees. And basically the extension is as follows. Instead of actually looking only at subarrays, I mean, we don't have just an array. We actually have like a tree. And we are looking at the paths which are from the root. Basically, this is a rooted tree. If you're, just to remind everyone, tree is a graph which has n-1 edges, and it's connected, so it has no cycles. So basically, there is a unique path from between every two vertices. So we have like a rooted tree, And basically what we want to do is we would extract all possible arrays which start from the root to every vertex. We'll find the f value of those arrays. So in other words, like the paths from every vertex to the root. And then we are going to compute the f function for each of those arrays. And what we are asked is to find the maximal possible value of this f function for any of those n arrays, because like we have n arrays which are from every vertex to the root. And yeah, we get all of those f values, and we want to output the largest such value. So the constraints are basically up to 5 multiplied by 10 to the 5, which is like 500,000. So that's pretty large. And you would expect to have a solution which is either linear or linear multiplied by a logarithm. Maybe if you have a very optimized solution, you would need linear multiplied by logarithm squared. But in general, you would expect something in these lines. So I guess let's get back to the solution. I'm going to quickly go to my presentation. So yeah, here I guess it's great to mention that recently CodeChef has actually have a competitive programming subscription-based course, which is pretty good. I'm going to open it up and speak about it for a bit. So yeah, it's on Unacademy, and basically what we have is, yeah, sorry about that. Basically, what we have is some people who are pretty good in algorithms and data structures, as they are basically like IOI medalists, also like ACM ICPC finalists, and yeah, like just top-rated coders in some of the online platforms. Also, some software engineers who work at some pretty good companies. So they basically teach some live sessions, which are interactive. So in a way, like you have the courses, and yeah, basically you can also ask questions during the sessions. And like the courses are structured. So after each course, there are some problems which are related to it. So yeah, that's, I mean, pretty good. And also, like, I guess the coolest thing is that the people who are teaching the courses are just very good at competitive programming. So you will definitely learn quite a lot of things. And yeah, I mean, for example, here you can see some of the courses. They're, in a way, they're structured. For example, like here you can see the courses that will be pretty soon. For example, the first one will be related to dynamic programming and recursion. So yeah, the courses are structured in this way, as you basically have some theme in which you can basically solve problems on. And again, like as an example, the next course will be by Arjun, and it will be for recursion and dynamic programming. Then there will be one by Ria, and it will be about sorting and searching. But yeah, in general, it's like different themes. And also one point here that I have to mention is that also during the lectures, there are some teaching assistants to whom you can actually reach out also after the sessions. So it's pretty cool, because if you have some doubts, you can just message some people and they'll like help you out. So I guess like that's a pretty neat way to actually learn. And also, like, there is a reference code, which is CodeChef. And if you go to the pricing, this will give you a 10% off for the 6 and 12 months subscriptions. So yeah, if you have like the CodeChef code here, it will give you a 10% off for the large subscriptions. And it will actually have an even larger cost reduction for the 1 month subscription to a flat $9.99 cost, which is pretty good. So yeah, I mean, I would definitely advise you to enroll, because it's from some top people. And if you want to learn something in a, like if you want to learn algorithms and data structures in a structured way, it's pretty cool. So yeah, let's get back to the problem, I guess. And I advise you check it out, like the competitive programming subscription. But yeah, I guess, so first, as I already mentioned, I'm going to be explaining how we are going to solve the problem if we just had a chain. So in other words, like a chain is simply like the root vertex having a bunch of children in like a large line. So yeah, basically we have the root in the beginning, And for example, those will be like the integers in every vertex. So yeah, the main idea is that when we have a chain, we can also think of it as a simple array, because we don't really have anything different from the normal case. So basically, yeah, we have like the chain, and let's say the root will be the leftmost position. We're going to be solving it in the following way. We'll first define two arrays. The first one will be left. And like the left array would be the following. So formally, it's like I, like L of position I is equal to I minus the smallest j, such that the subarray j to I is non-decreasing plus 1. But I mean, this kind of looks weird if you proceed like that. So in simpler words, it's just starting from one position. For example, like look at this 4. It would be the length to the left of the longest subarray such that it's non-decreasing. Or in other words, like if we just compute it for like this array I have shown here, it would be, I mean, the array is like the one above, and the L is the array below. So yeah, in other words, like for 1, it's just 1. Then for 1, 1, it's 2, because 1, 1 is like a valid subarray, and it has like length 2. Then for 1, 1, 5, the largest subarray that ends on 5 is basically 1, 1, 5, because it's non-decreasing. Then for the next position where we have like the 3, it's just 1, because I mean 5 is greater than 3, so we can't really include the 5 because it will break the non-decreasing subarray. So yeah, in this way, we basically just fill out the left array, and that's just a simple for loop, which is, yeah, basically L of y is equal to the previous value plus 1 if we have like a valid pair, basically if the current element is greater or equal to the previous one, or it will be just 1 if the current element is less than the previous one. But yeah, it's pretty simple to compute in a linear path. And then similarly, we would have a right array, which I guess you already figure out what will represent, is basically the largest j greater or equal to I, such that the array from I to j is non-decreasing, minus I plus 1, which is in a way the length from a certain position to the right of the largest subarray, such that it's non-decreasing. So yeah, in other words, again, similar to the last example, I have represented the R's. So like you can see that for the first position, it will be 3 because we have 1, 1, 5, which is the longest subarray. Then for 2, we have 1, 5, which is the longest increasing subarray, and like so on. And I mean, basically, to compute this, we basically do the same as in the previous case for like the left array, but the only difference is that we are going to start the loop from n to like 0, from n minus 1 to 0, because like we are basically looking at the next position and getting the next answer plus 1. But again, that's an additional linear path, which is pretty simple. So okay, after that, I guess how can we find the answer before that? So yeah, basically, you can convince yourself, I mean, I'm going to explain it in more detail, that the answer will be the maximum of left I plus right j for any I and j, such that a is less than j, such that ai is less than or equal to aj. Okay, this may look kind of confusing, so I'm going to explain it again on this sample. So basically, we want to choose two positions. For example, let's look at the 8, and then let's look at the 6. And I mean, like if we choose every two possible positions, this will basically represent in the problem statement, the end of the first subarray and the beginning of the second subarray. And we know that to like keep the non-decreasing criteria, we want to have like 6 being less than or equal to 8. So basically, we wanted to have like the left bound, the end of the first subarray being less than or equal to the beginning of the second one. And I mean, like if we just iterate through all possible beginnings and ends, and then like look how much they can be extended to both sides, which will be basically represented by right and left, then if you just try all possible choices for I and j, you would have went through, I mean, all possible choices for subarrays, So this will be enough for you to actually solve the problem. So in other words, like another way to think about those two arrays that we defined, which are right and left, is the number of elements, like the number of elements we can extend a certain position to the left and to the right so that it will keep the constraints. Okay, so basically, going back to this slide, we can, I mean, basically, we already have like left and right computed in linear time because it's just a simple pass. Just the most simple solution would be to fix every possible I and every possible j, and then check whether this criteria holds, which is like a constant check. And like, if it holds, we can basically add like, compare the answer with left of I plus right of j. So yeah, that's like a solution, but it's n squared because we try all possible i's and all possible j's. But also, you can kind of, I mean, at least I think this problem kind of resembles either the longest increasing subsequence or the inversion counting problems. Because in a way, like we want to find some maximum which depends on two values. Like basically the inversions are pretty similar to this, but the sign is different. But I mean, in a way, it feels kind of similar to counting inversions and or longest increasing subsequences. So I guess this should suggest you to actually think about the solutions for those two problems. But I mean, actually, there is like a certain solution which basically uses segment trees, which is pretty easy. So I'm going to go into it, and I'm going to explain more details about how to actually solve it. And it's in n log time because you'll see. So okay, basically this should suggest you that the solution for this problem, like on the chain, will be pretty similar to counting inversions with segment tree. Because like actually when you count inversions, you can do it with merge sort, but also you can do it with just a segment tree or a Fenwick tree. It doesn't really matter. And the solution I'm going to be describing right now is the one where you count the inversions with Fenwick tree. But like I'm going to apply it to this problem. And yeah, let's get straight to it. Okay, so basically the main trick here is that we use a segment tree on the values and not really on the array. By values, I mean like the key of the segment tree will be the value and not the position. So in other words, if you think of it, I mean, one abstraction would be to actually think of, normally you would have like an array, and we tend to represent arrays in a horizontal manner. And like this way, I guess the segment tree will be like horizontal if it was on the positions. However, when you think about segment trees on values, you can tend to think of them as like something vertical, which is, imagine like you're gonna have the array and you represent it as a histogram, for example. Then when you have segment tree on the values, I mean, you have like for every value, like every possible value, there will be like a certain position in the segment tree. So yeah, I mean, I guess it's kind of hard to just think about the abstraction. So let's get into some more details. The steps of the solutions are as follows. First, we are going to compress the values because in the problem statement, we actually had values from minus 10 to the 9 to plus 10 to the 9, which is, I mean, pretty large to create a segment tree. There are alternatives, like we can use some balanced binary search tree, or we can use dynamic segment trees. However, the most simple solution would be to actually compare them, to just compress the values, because we don't really care about how large the values are in this problem. We only care about the relationships between them. So it's fine to just compress them. And let's assume that after compressing the values, we would have every element in the range from 0 to k, where k is less than or equal to n. Because, I mean, we are sure that we will have at most n elements when we compress everything. So yeah, that's like the first step. Then the second one is we are going to initialize a segment tree, which basically will will be for the range from 0 to k. So in other words, as I said, it's on the values, and every leaf will represent one of the possible compressed values. So yeah, after that, the whole solution would be just a for loop with 2 lines, which is written here. And let me explain what will happen here. So basically, initially, our segment tree will be empty. So it will just have zeros for every possible value. Then what we're going to do is basically we go through the elements one by one, and we make the answer. So yeah, basically here we have one candidate for the answer on the first line in the loop. I hope you can see my cursor, but yeah, like the first line in the loop is basically we compare the answer with right of the current error of position I, which is the amount we can extend to the right, plus query max for the range from 0 to AI, where AI is the current value. And basically, what this segment tree will hold, it will be a max segment tree where every key or like every leaf will contain a value which is the largest possible left I, such that it ends on AI. So in other words, like after we have basically computed this candidate, we would update the segment tree at position AI with the LI. And then in the query for the next positions, we are only going to consider elements such that their AI is smaller, because like in the segment tree, again, it's on the values. So in a way, like this way, the range from 0 to AI will just represent a previous position is less than or equal to the current one. So yeah, but basically like that's literally the solution for when we have a chain. And I guess here it's a good moment to ask for questions, because if you aren't very familiar with this approach, it may be a bit weird at first glance. So yeah, I'll just wait for, I don't know, like a minute or a couple of seconds to just see whether there will be some questions. But it seems that there aren't. But yeah, I mean, like if you have some questions further in the discussion, I guess you can just leave them in the chat. And I'm going to go back to this slide, because like the next part is basically how we are going to extend this solution to trees. And actually it turns out that it's not that hard, because okay, yeah. Basically for trees, there are 2 solutions. The first one is with segment trees, and then the other one is the intended one, which is, a bit trickier, but it's way simpler to implement because you don't really need any advanced state structures. And it uses one trick, which is normally used when you're talking about longest increasing subsequences. But yeah, it can be also applied to this problem. And it's pretty neat to hear. So yeah, I'll first explain the segment tree solution because it's just standard. And normally in a contest, if you just don't come up immediately with like a nice solution, you can easily call this, because you can easily just have the max segment tree as a template. And yeah, it's not that hard to implement. Okay, so the first trick, okay, before actually going into solution, let's just remind ourselves what the problem for trees was. Instead of actually having like subarrays, now we have a tree. And basically now, instead of just subarrays, we are looking at paths. So in other words, we are looking also, like there is this additional criteria that we are looking at paths which go from the root, which is basically vertex number 1, to some other vertex. So the paths are in a way like vertical, because they just go down, and you can't like have some paths which don't start at the root. So yeah, like in other words, because like now we change from a chain to a tree, and normally it's easier for people to think of trees as something vertical, like the root being on top, and then you basically having some children, the abstraction will change a bit, and instead of having like left and right, we are going to compute two values, which are basically up for some vertex I and then down for some vertex I. And those will be computed as follows. Basically up. So here I am using something like C++, and like up will basically be if the parent's A value is less than the current A value, then the current up will be, here I actually have a typo, sorry about it. So here it should have been, yep. So let me just, I'm going to change it after that, but basically, if the A of the parent was less than or equal to A, then the up would have been the up of the parent plus 1. So here, instead of u, we would have parent. And if that's not the case, we would just have 1. So yeah, like that, this way we're computing the up, and it will mean the length of the longest path going up such that it's ending at the current position, and it's non-decreasing. Okay, so that's the up. And similarly, we'll actually consider down, which will basically be corresponding to the right value. But when we have a tree, we technically have a slightly different thing, because we actually have multiple children. And when we had a chain, we only had one child. So we could have just gotten one of the children. But actually, when we have a tree, it's not that much different, because we just have a bunch of children. And if we have already computed their down values, we can just get the largest one. Because we are looking at some vertex, it has some children. We've computed lengths. So we can see the valid children, and the valid children is such child that its A is less than, such that its A is greater than the A of the current vertex. Because in a way, the current vertex will be the first one, and then the other vertices will be basically, the vertices below or the vertices down will have increasing values depending on compared to the current one. So yeah, this way we have some of the children will be available while some others won't really be available. And basically the down of some vertex will be 1 because of the current vertex plus the maximum of the downs of the available children. And if this set is empty, we are just gonna say that it's 0, because if basically there are no possible children below, or basically if there are no children at all, then we just get we just get the current vertex as the down part. So okay, basically we have this part, and we can compute it with one DFS, which is just start a DFS. When you enter a vertex, you basically compute the new up value. Then you go to all of the children, you compute their up and down values. And then you go, basically after computing a certain child, you compare the current down with 1 plus the down of this child, but only if the AU is less than or equal than AV, where V is the child and U is the current vertex. So yeah, that's pretty much it. It's just one DFS, and that's a relatively simple thing to do. And now I guess the harder part is actually how to incorporate this segment tree on values to this problem, because now we actually have a tree, while in the previous case we only had an array. But it turns out it's not that much different. Okay, actually I completely forgot one part. So now what the answer would be, as we are basically looking at all paths, the answer can be represented as follows. We want to pick two vertices such that the first one is an ancestor of the second one. So in other words, both of them stay on the path from, basically if we just go to the parent, and so on, we will reach the second one. And let's say that U is the ancestor and V is the vertex below. And if we basically iterate through all possible U and V such that AU is less than or equal to AV, and compute the up plus down value and find the maximum, we are going to basically solve the problem, because those are all possible ways to choose the subarray that we were talking about. And again, similarly to the last case, this will yield a n-squared solution because up and down can be easily computed in linear time. And then, I mean, we just compute them. We have them stored in some array. And then we just choose all two vertices and check in some time whether one of them is answer of the other one, which can be done easily in constant time. And then also check whether the value of the first one is less than or equal to the value of the second one. So after if that's the case, we just compare the answer with up u plus down b. But yeah, I mean, the problem with this solution is that it's quadratic. And now I'm going to explain how to actually incorporate the segment tree on values to solve this problem. It's again a simple DFS where, let's say ds will be like the ds which I have bolded will be our structure. So similarly to the previous case, initially, let's ds be the structure if we consider the array from, I mean, in some sense, we want to actually convert the tree problem to the problem when we had a chain. And like when we're going to keep the following invariant. When we are at vertex u, we are basically going to have this data structure, which will represent the segment tree on values for the path from the root to the current vertex u. And I mean, if it represents it, we'll basically have the same thing as in the case for array. I'm going to go quickly back to it. So before that, it's basically ds.query from 0 to au. And ds.query is basically the maximum for this position. And we are going to add down to it because ds will represent the largest value for the current vertex. And so in a way, it will be like the largest value plus the down of the current vertex. So yeah, that's like a candidate of the answer. So after that, what we are going to do is we are going to see what was the previous value at the position of au. So I mean, old val will be the previous up value for the leaf at au. I have just done it as a query from au to au. But yeah, this should give us the value in the leaf for au, because again, ds is a segment tree on the values. So yeah, I mean, we compute the old value and we keep it in some variable in this vertex. And then we are just going to update au with a new value, which is equal to the maximum of up of this position, because or in other words, in the previous case, here we had left and old value, because I mean, if it may turn out that the old value was better than the current up. So yeah, in other words, if that's the case, we don't really do the update. And then what we do is simply go for all children and run a DFS for each of them. But here comes the tricky part. I mean, it's not that tricky. It's relatively simple. After we have actually done this update, we are going to roll back it. And the rollback is as simple as just having updating at the previous position with the old value which we had. So in a way, we basically kept this old value only to be able to roll back this data structure. I mean, when you do a DFS, you're basically going through a child, and after you visit everything, you somehow need to remove it, because it will, after you visit the whole subtree, you won't really have any additional children or in the subtree. So it will never be needed in any path, after the ones we have already computed. So in a way, you can just roll back this update so that you will represent the previous path. So yeah, I mean, in a way, we, as an abstraction, we first, in this DFS function, which will be the, so yeah, okay. First, we have one diff, just going back to the whole solution. If you got confused, we have two DFSs. The first one is to compute the up and down values. And then we'll have an additional DFS, which will actually solve the problem. And here is the second DFS, which is the solve DFS. And yeah, as an abstraction, first we are going to consider the candidate for the answer, which is the largest up value on the path from the root to the current vertex. plus down on the current vertex. So yeah, this will consider some of the candidates for, this will basically consider the candidates such that the second subarray starts at the vertex U. And after that, what we do is basically, for the rollback, we would need this old val. So yeah, sorry about that. So for the rollback, we would need this old value. So we first extract it. I mean, that's like just the value in the on this leaf. And after that, we just update with the new value and go for all children. And like here in the children, you would again compute everything. And after like you finish the child, you would roll back the update from the child. And you would still have like the same invariant of the DS, just holding the answer for the paths from the root to the current vertex. So yeah, after that, that's literally it. And I mean, the complexity will be n multiplied by logarithm, because we have just a constant number of updates in every vertex. And in the DFS, we have like constant number of queries on the tree and constant number of updates on the tree for every vertex in this graph. So in other words, we basically have n multiplied by the complexity of the data structure, which is log. So we have complexity n log. And it's just the extension of the subarray solution to a tree. And it's a pretty neat thing to have, because it's actually used sometimes in other problems where you basically have some structure which you update, then you solve all children, and then you roll back the structure. So that's a nice trick you should probably remember. That's like the most general approach that's used in this problem. While the second general approach is basically the segment tree on values. But yeah, that's pretty much it for the segment tree solution. And now I'm going to go to the other solution, which is basically the intended one. And the main idea is that we are going to convert the segment tree into array, and we are just going to have a binary search there. So yeah, here is a pseudocode of it, which is basically we are going to do a binary search. So we have like this DP array. I mean, it's not really, in a way, it's kind of a dynamic programming. So yeah, we are basically going to binary search the AU, which is like the value of the current vertex, in the DP array. Then we are going to basically position will actually hold the optimal up for AU. And I'm going to explain why in a bit. And so then the candidate will be just position plus down. And the all value will be just DP at this position pulse. And then what we basically do is, yeah, actually, I again have a typo here. So yeah, don't look at this part. Let me check whether I can actually. So yeah, here we shouldn't have had like up. It should have been something different. Basically, here we should have had A of U and not up of U. Sorry about that. So yeah, here we should have had A of U. I just want to like say it now before I explain what exactly DP will hold. But in general, like it's pretty much the same. We find the all value, then we do the update on this data structure, which I'll explain in a bit. And then what we do is basically we roll back again by just saying that DP of this position will be again all value. Like, I mean, after going through the children. So yeah, I mean, like the tricky part of this solution is actually just, I mean, of this conversion is basically what DP will be and what our data structure will be. But I mean, I guess it's already clear that the implementation of this solution is way simpler than the implementation of the previous one, because instead of a segment tree, you can just have a lower bound, technically an upper bound for the position. And after that is just editing some positions of an array, and it's just simpler to implement. But yeah, let's go to what this DP will represent. So yeah, basically, DP will be the minimum ending value such that there exists an increasing subarray, actually a non-decreasing subarray, because we can also have less than or equal values, such that its length is equal to I and it's ending on the value dp of I. This may be a bit confusing because, like, I mean, basically the main idea is that initially, okay, so initially dp will just have infinity for every I. And like what dpi will represent, it will be the minimum value such that, so in other words, like I will be here the length, or like in other words, the answer. And what we want to do is to keep the minimum value of a subarray that ends on, okay, yeah. Let me try explaining it in a nice way, because that's, to be fair, it's a bit tricky. So yeah, we'll have, so dp of I would be the minimum value such that I is basically the length of some subarray, and this in some increasing subarray. And having I as length, we basically have like AI as the last value. And that's useful because when, I mean, when you actually do a query, you can just, you just want some positions that have a less or last value than the query. Because like when we were looking at, I'm going to go back to this case. So basically, like when we are looking at the position left and the position right, we were basically looking at some values such that they had a lesser AI than the current one we are doing. So in other words, like in the query, we basically looked at the range from 0 to AI. So I mean, like the positive thing about this DP, which we are doing, is that it will be non-decreasing. So in other words, like we can just find the largest value such that it's less than or equal to the one we are querying. And this way, we are basically gonna, if we just look at the position, as we keep the invariant that the position is actually the length of this array, we can just find the last value that's less than or equal to I, and our answer will be this position. So yeah, after that, the update is relatively simple. We just, I mean, technically, when we have an update of AI with Li, we just need to have, we basically just compare in our structure the position for Li, and we make it to be equal to the minimum of the previous Li and AI, because this is fine for you to actually do the update. And yeah, this way you can do a binary search. But honestly, like, I think it's a pretty clean thing to have. But the problem with it is that it's, I mean, normally when you're in the contest, you would have to like think about the details in this solution. And like if you just use a segment tree, you'll be fine. Also, something that actually didn't mention this problem, but I guess it's a pretty useful thing, is that you can see that all queries are from 0 to some position, for example, in this case, AI. So instead of having a segment tree, you can just have a Fenwick tree. And basically what you do is, I mean, it will be a max Fenwick tree, which technically works as fast, even sometimes faster than binary search. So yeah, it's, I mean, you can argue which one is actually better, having like the DP or like, or just like the Fenwick tree. Although, I mean, still the Fenwick tree is a bit better. Pardon me. I mean, the array plus binary search will probably be still a bit better because you just have one binary search there, and it's not, I mean, in the, basically like in the Fenwick, where you have like an update, then you have like a query, and you also have a rollback. And that's, I mean, kind of tricky because like all of them are log, while in the case of the binary search, we just have binary search to find the position, and then all of the updates are constant time. But yeah, I mean, like, it's a good thing to know, and you can refer to the editorial, because I think the solution there is exactly this one with the binary search and not the segment tree. So there are more details about the solution, but I think like the one with segment trees is easier, because you can think of the segment tree as a black box. And yeah, it's also, at least in my opinion, it's a bit more useful, because you would be able to actually apply it to some other problems, where again you have like some paths which are from the root to some other vertex. And yeah, like in general, I think that's pretty much it, because like after that, basically like, that's the correctness of the DP. And I mean, basically, if you just keep this invariant of I being the length, then the updates and the queries are just a binary search, and then some constant updates at some certain positions. So yeah, I guess like if you have some questions about this, feel free to ask. And overall, thanks for watching. Again, like, let me remind you about the CodeChef subscription and the plan, as it's pretty good. So if you have some time and you want to like actually try it, I definitely advise you to go for it. So yeah, I guess that's pretty much it. Thanks for watching, and I guess see you next time. Although, like right now, I guess I can answer some questions if there are. And yeah, also finally, I guess maybe something that's needed is like feedback. So yeah, like I would really appreciate if you could fill the feedback form, which is pretty short. So it should be linked here in the video, also on like the Facebook alternative. So yeah, this will be pretty useful. So I would greatly appreciate if you can fill it out. And again, like, thanks for watching. Maybe I'm going to just wait for some questions. Actually, I can also open the YouTube and check them out this way. So yeah. Like looking at the YouTube, it seems that there are no. So yeah, I mean, it seems like there are no questions. So I guess let's just end it here. Thanks for watching again, and yeah, see you next time.